Hello, the purpose of this video is to introduce the topic of lecture 36 of mcs360 Introduction to Data Structures. Now what's the topic? Red-black trees. So we will construct a red-black tree for an example, a sequence of numbers starting with 42, always a good number, then 93, and continuing, ending with 16. So what is a red-black tree? A red-black tree is a binary search tree where the nodes are colored either black, either red. So we start with the number 42, which will be colored in black, so the root is always black. It's a binary search tree, so when 93 comes in, we insert it to the right of 42 and color it red. If we do not have colors, then we can use this convention. Red nodes are always have hollow rings. Black nodes, they have solid rings. Hollow rings for red nodes, solid rings for the black nodes. So the next number is 25, so 25 comes to the left of 42 because it's less. So we have this binary search tree. Everything at the left of the root is less than the value of the root. Everything that is at the right is larger. Next number is 22. So 22 is less than 42, less than 25, so it goes to the left of 25. And it is colored red because it's a new node. So this is our binary search tree. But now we violate one invariant of red-black trees. A red node can only have black children. So here we have a red child of a red node that has a black child. So that violates the invariant of a red-black tree. We can fix this by coloring 25 black if we can color also the sibling black. And here we can make 25 and its sibling both black. Obtaining this tree. So here you recognize now that every path, so we have two paths, one going to the left, one going to the right. Every path has the same number of black nodes. So that's the other important property of red-black trees. The number of black nodes on every path leaving the root, ending at every leaf, that path has to have the same number of black nodes. Let's keep that in mind. So we continue. We inserted the first four numbers. 18 is less than 42, less than 25, less than 22. So it goes all the way to the left of 22. So, and we end up with this. We again have a red node with a red child, but now we are in the situation where 22, if we would color that black like we did here, the 22 has no sibling. So if you would color 22 black, we would have 3 black nodes in this path, and we cannot do anything here because there is no node here. So we cannot color 22 black. But observe that if we would color 22 black, then 25 could be red, because 25 would then have a black child, cannot have a red child. Now 25 cannot be red, but as 22 is black, then it can be red. So let's do that. Let's make 25 red and 22 black. Then we will see that we still have a constant number, so the same number of black nodes along every path. So we still have 2 black nodes on every path. Okay, 30 is the next number. 30 is less than 42 but larger than 25, so it goes to the right of 25. And since it is a new node, I will color it red. So now we still have the problem, we again have the problem actually, that this red node 25 has a red child. But you see that this red node here has a black sibling. So, and you can see actually along this path, it's actually a new path, that there's only 1 black node. And here we have 2 black nodes, here we have 2 black nodes. So making 30 black, the same color as 22, will solve our problem. So now we have a red-black tree with 3 paths. So 1 path here, 1 path that ends in 30, 1 path that ends in 93. Red children, red nodes have only black children, and we have the same number of black nodes along every path. Finally, 16 is our last number. So 16 is less than 42, less than 25, less than 22, less than 18. So it goes to the left of 18. So now we obtain this binary search tree, and we have a red node that has a red child. The red child has no sibling, and the sibling of 18 is also missing. So last time that we had a situation like this, we could swap the colors. But if you would do this here, if you would color 22 red, 18 black, then we would have 25, a red node that would have a red child, that would violate the condition. So we cannot resolve this violation against the invariant by just changing colors of the nodes. The way we can do it is by rotating. So we can rotate this left tree so that 18 occupies the spot of 22. So 18 here becomes the place where 22 was. So I will not change the coloring code. So 16 is at the left, remains at the left. So we have this left rotation. Then the sibling of 22 was 30. So that is now the sibling of 18. So you you observe now that we still have the same problem. Actually, it may have gotten worse. We have a red node that has a red child, but also actually this node has actually a red child as well. So we seem to have made it worse. But observe that here 18 did not have a sibling. Now, because of the rotation, 18 actually now has a black sibling. So we could color 18 black and change then the color of 22 from black to red. Let's do this and verify that that solves our problem. So 22 becomes red, 18 is colored black, is a sibling of 30, 25 can remain its color. So we end up with a binary search tree where the colors of the nodes are either black or red. The root is colored black. The red nodes have only black children. And what is important for the balancing is that along any path, so here we have 1, 2, 3, 4 paths now, you can count that the number of black nodes that you encounter is 2, the same number for every path. So this was a short introduction to red-black trees. As always, the slides for the lecture provide more background, and then there is also the posted code.